Welcome to the public AI Cafe on May 31st. Great you all are coming. Here is also our speaker today, Fabrizio Sebastiani.
Sebastiani.
So,
like Sebastian with an ending I.
That's easy. Sebastiani. From the Institute for Science and Technology of Information, Italian National Council of Research. Today the talk is about Exit the Needle, Enter the Haystack, Supervised Machine Learning for Aggregate Data. I'm Carmen McWilliams, I'm your moderator and cafe manager, and we are all part in this AI research project called AI for Media. And it's important, as always, this session is recorded. And the link for this recording you will find afterwards in our cafe channels, but the speaker has to give permission for this, so it can only be there if Fabrizio says yes.
Sure,
and no
sure.
You say yes?
Yes.
Okay. And no confidential information shall be shared in this cafe. All speakers express their personal views and opinions. This is not necessarily the official AI for Media project opinion. And as you know, this cafe is about sharing knowledge and meeting interesting stakeholders from various areas of AI research and application. Most important, it's interactive, and whoever joins this cafe may ask questions. There is a control panel on the right side. Please send us these questions. It will be text messages. I mean, just send them to us, and I, after the presentation, will read them to the speaker, and so you hopefully get your answers then. But we first will have the presentation, then the questions. So shortly, I introduce the speaker. Fabrizio Sebastiani is a director of research at the Institute for the Science and Technologies of Information of the Italian National Council of Research, where he leads the AI for Text group. Formerly, he was a principal scientist at the Qatar Computing Research Institute and an associate professor at the Department of Pure and Applied Mathematics of the University of Padova, Italy, from 2005 to 2006. His research interest lies at the interface of machine learning, NLP, information retrieval, and data mining, with particular emphasis on learning to quantify, technology-assisted review, authorship analysis, cross-lingual learning, and their applications. He's a senior associate editor and the acting editor-in-chief for ACM Transactions on Information Systems, a founding editor and former co-editor-in-chief of Foundations and Trends in Information Retrieval, and a former member of the editorial boards of numerous journals in the field. He is the editor for EMEA of Springer's Information Retrieval book series. He has been, among others, a general chairman of ISTI-CNR 2003, SPIRE 2011, ACM, CGIA 2016, ECIR 2021, and CLEF 2022, and the program chairman of ACM, CGIA 2008, ECDL 2010, and ACM Affirm 2020. So this is very impressive, and I'm very happy you're here today with us, and I will now shortly give over to you. And again, great also to all participants that you're here. Use the chance, ask questions. We are really looking forward to them. So, Fabrizio, it's now your turn, your stage. I will slowly fade in the background.
Thank you. Are you seeing my slides?
Yes, perfect.
Okay, good. So thank you very much for Carmen for inviting me here. Thanks to all of the attendees for joining this talk. It's a talk that is going to be about surprise machine learning, about supervised machine learning, and about a sort of a special type of context, of application context in which supervised machine learning can help. Okay, so it's about indeed supervised machine learning for aggregate data. So the idea is that there are a number of a special type of application contexts where classification technologies are useful or are used, in which our interest is not really at the individual level, but at the aggregate level. Okay, so what do I mean? Interest at the individual level means that for classification, so when we classify an item, a data item, say a document or anything, okay, so it means that we are interested in the class label to which the item belongs, to the class to which the item belongs. While aggregate level means we are not very much interested in individuals, but in populations. And especially in the classification case, in this case, we are interested in how many individuals belong to a certain class. We are interested in the percentage of individuals that belong to a certain class. And indeed, this kind of concern is typical of many fields of human activity, because many fields of human activity, such as here the social sciences, political science, or epidemiology, ecological modeling, market research, they are mostly interested in aggregate results. They are interested in an analysis which is at the macro level rather than at the micro level. So for instance, epidemiology, an epidemiologist is not interested in individual patients, but is interested in how, say, a virus is distributed across a population. So there is a focus on the population instead of on the individuals. A market researcher, operating, say, for McDonald's, may be interested in whether how many people, what is the fraction of the population that likes, say, onions in their cheeseburgers. But they are not interested in whether I, Fabrizio Sebastiani, an individual, likes onion in my cheeseburgers. So in these fields, essentially, we don't care about individuals. We care about populations. And this is why the title of this talk, we don't care, unlike IR, say, information retrieval, which, within search engines and the like, searches for the needle in the haystack. This is a typical metaphor of information retrieval. Instead, we don't care in these applications. We don't care about the needle, but we care about characterizing the haystack. And this is what quantification or learning to quantify is about. So this is a machine learning task that stands to classification as aggregate data stands to individual data. So quantification or learning to quantify or supervised prevalence estimation, as it is sometimes called, has to do with estimating the percentages, of a population that belong to a certain class. And today's talk is indeed an introduction to this field, to this task, and to its potential applications. So, in order to get me started, let's start with an example. Okay, so we may assume that we have a set of product reviews of a certain, say, of a certain item, a certain book, and we want to estimate, estimate the sentiment about this book. So, for instance, we might be interested in finding out, how many of these, textual comments express a very positive opinion about the book, how many express a positive, how many express a very negative comment about the book. Okay, so indeed we are interested in estimating the distribution of sentiment. So here this is represented as a histogram in which the blue bars are, let's say, the true percentages. So for instance, we see here that something like 42% of the reviews are very positive, 28% of the reviews are just positive, and the like. Okay, of course, we don't know these percentages, so these percentages need to be estimated, because, say, we don't have let's say, so we are talking about textual comments appearing on posts. We don't necessarily talk about product reviews appearing on Amazon, because these latter have, say, scores in terms of 1 to 5 stars. So we here assume that we don't have these scores from 1 to 5 stars. We just to estimate them, and estimating these percentages, okay, can be done via supervised learning, as we all know. And the idea is that the perfect estimation is the one where the red bars that represent the predicted percentages are identical to the blue bars. Okay, so here we are in the presence of a red histogram that approximates reasonably well, but not perfectly, our sentiment. Okay, so I want to actually focus on one word, distribution. You may all realize that this is a probability distribution, okay, because we have a total of 100%, and so the idea of learning to quantify is that we need to estimate a distribution, a probabilistic distribution. And so this essentially means that our evaluation criteria will be, the measure that we will use in order to estimate the quality of our prediction will be a measure that compares distribution, a measure that estimates how well a predicted distribution fits a true distribution, a measure, say, like Kullback-Leibler divergence or the like. So let me give you a few use cases, for quantification. So here we have a certain amount of, say, tweets. Okay, so we are in this period, say, there are political elections in a certain country. Many people tweet about these elections, and via prediction mechanism, we can try to interpret all of these tweets and map them to parties, okay, so that we can estimate what is the, let's say, the sentiment towards certain parties. Okay, so in this histogram, we basically see that something like more than 45% express support for party A, something like 10% express sentiment for party B, etc. So a very different application. Okay, so suppose that we have a blood stain, a stain of blood that we need to analyze in the lab, and suppose that by putting this under a microphone, we can recognize blood cells. Okay, so one idea, for many medical applications, for instance, for diagnosing leukemia or the like, what we would need to estimate is the percentage of all the blood cells that we are seeing in this blood stain, in this blood sample. Try to estimate the quantity, the percentage of white blood cells, okay? Because this, of course, is conducive to a good diagnosis of leukemia or related illnesses. For instance, we might also want, out of the total percentage of white blood cells, to estimate the quantities of different types of white blood cells, such as neutrophils or basophils or the like. Surprisingly enough, there are applications also in astrophysics. Okay, so in astrophysics, there are some scholars in astrophysics who actually use telescopes in order to record the shower of gamma particles that falls on the Earth. And out of all of these particles, they are interested in finding out the percentages of particles that have certain energy levels. Because this is conducing to estimating where these particles come from, and what type of particles they are. So again, this is a type of applications in which we are not interested in the fates of individuals. We are not interested in individual gamma particles. We are not interested in individual blood cells, etc. But we are interested in their quantity. We are interested in their percentage. And learning to quantify, also called class prior estimation or the like, exactly tries to estimate these percentages. Exactly tries to estimate these quantities. Okay. So, this is a task which has had a certain sort of a fragmented history, because the history of this task is highly non-linear. It's been essentially discovered and rediscovered from within different disciplines. And we can recognize a first stage in this historical development, and one where machine learning people essentially spoke of the estimation of class priors. And here the goal was not using these class priors in themselves, but using these class priors in order to make classifiers more robust to the presence of prior probability shift. Okay, so trying to, in a sense, tune a classifier to situations or to unlabeled data that were characterized from prior probability shift. In other words, to make classifiers that are better attuned to the data to which they need to be applied. And here, there was a very influential work, which is the paper from Marcos Herrens in 2002. And a few years later, we can witness the emergence of a second stage. So it's interesting in what people started to call quantification from within data mining and text mining. Okay. So the goal here was estimating quantities and trends from unlabeled data. So for instance, estimating the quantity, the percentage of requests of support for printers, out of the total of the requests for support, that a hardware company was receiving from customers. So what characterizes this second stage of development from the first is that here we are interested in the quantities in themselves. Okay, so quantification as discovered or rediscovered from data mining places a focus on these quantities as interesting in themselves rather than as functional for improving other type of machine learning methods or processes such as classifiers. And it is indeed the application from these fields that have provided the major impetus behind the research in quantification that has occurred in the last, say, 10 years. So one question that many of you might wonder now is whether, it's the strategy of applying classify and count is an optimal quantification strategy. What do I mean by classify and count? It's essentially the trivial method, of classifying, say, training a classifier, on training data, applying the classifier to all of the unlabeled data, counting the number of unlabeled data items that have been assigned to a certain class and normalizing. Okay, so this is the estimated percentage. So is this classify and count the optimal quantification strategy? And the answer is essentially no. The reason is that, sure, a perfect classifier is also necessarily a perfect quantifier, but we never have perfect classifiers. We have good classifiers, and a good classifier is not necessarily a good quantifier. And I'm showing an example here, So here I'm displaying two possible classifiers, H1 and H2, that are classifying the same test set. And classifier H1 makes 25 mistakes, so 5 false negatives and 20 false positives, while classifier H2 makes 30 false negatives and 30 false positives. Okay, so which is the better classifier? Certainly H1 is the better classifier because it makes fewer mistakes. Which one is the better quantifier? The surprising answer is that H2 is the better quantifier because it makes a balanced number of mistakes. It makes the same amount of false positives and false negatives. And when it comes to estimating the percentage of items that fall in a certain class, false positives and false negatives cancel each other out, And indeed, you may realize here that essentially the number of positives here, the number of actual positives was 170 plus 30, as in this first column, and the number of predicted positives is also 70 plus 30. as in this first row. So H2 is essentially a perfect quantifier, despite the fact, that H1 is a better classifier. Indeed, here we have, for H1, we have 115 predicted positives, which is 95 plus 20, against 100 actual positives. Okay, so the true percentage, that should have been estimated is 16.7, and indeed the predicted percentage is 19.1. So paradoxically, for quantification purposes, we should prefer H2 to H1. So this, in a sense, shows that quantification, learning to quantify, is a task in its own right. We should be tackled as a different task from quantification, because first of all, it requires evaluation measures which are different from those of classification. Because here we need to estimate the fit of distributions, and we don't need to estimate, the number of mistakes. And the second thing is that, the same model that when two models are trained, one model may be better at classification, but the other model might be better at quantification. So this is a good enough justification to say that we should tackle these two tasks as two different tasks. And this is a summary of how the two tasks look like. Both tasks start from a training set of labeled individual items. But the difference is that one, in classification, we have to train a classifier, which is a function that maps individual items in classes. In quantification, we have to map a quantifier, which is something that maps sets of items into distributions, which are here denoted as points on the probability simplex. And again, one similarity is that we are, using feature vectors. But here, we need a quantifier needs to take, let's say, a classifier needs to take in input ideally a representation for an individual. Here, a quantifier takes as input, a sample of feature vectors. The type of errors is also different, because the typical errors in classification are false positives or false negatives, while in quantification, the error is either underestimating a class, a percentage, which in statistics or in probability is normally called the prevalence of a class, either underestimating or overestimating it. And also the assumptions according to which research is carried out are different. Okay? Because in classification, when we study classification, we typically make the so-called IID assumption, the assumption that the training data and the test data are drawn identically and independently from the same distribution. In other words, that both training set and test set are two random samples of the same distribution. This is very different from quantification, because if we had to make the IID assumption in quantification, then quantification would be a trivial problem, okay? Because if we had to make the IID assumption, well, if say the positives in the training data are 30%, we might probably assume that the positives in the test data are also 30%. But instead, in many different real application scenarios, the IID assumption is not satisfied, and indeed, many such scenarios are characterized by what we call prior probability shift. It means that the prior probability is the class prevalences shift. It means that they differ from training data, test data. Say maybe in the training data we have a 30% fraction of positives, but in the test data this fraction has become 70%. So, as I said, the need to perform quantification indeed arises because prior probability shift is indeed possible in real application scenarios. And this is a plot that basically shows that prior probability shift is there in real data. This is data taken from the so-called Reuters corpus volume 1. So this is a snapshot of 1 year of news produced by Reuters. Okay, and this is in particular a snapshot. Sorry, this is a snapshot on the E21 category that I can't exactly recall what it means, but this is types of journalistic news. So maybe say acquisitions and mergers. So in this category, you may see that the true distribution of the examples of this category goes up and down throughout the year. Okay, so here on the x-axis, you see that there are 52 different weeks because this is a 1 year snapshot of news. And you see that at this point, at about the 18th week, there was a peak of news about which belonged to the E21 category, but a few weeks later, we had a negative peak of them. So the blue line actually indicates the true prior probabilities, and the other lines, the red one, the orange one, and the green one, indicate the results of different quantification systems. Okay, so different systems that attempt to estimate these quantities. Okay, attempt to monitor this temporal trend. And of course, I mean the curve, which best fits the blue curve is the better quantifier, which is in this case is the red curve. By the way, this is a real experiment that we ran a few years ago. We had the classify and count, too, but classify and count was falling essentially off the scale, so it's not represented here. It was performed very badly, And as I mentioned, if we indeed knew that there is no prior probability shift in the data, classifying count would probably suffice. Maybe classifying count, let's say, built with a specific classifier that is, say, optimized for generating output, which is fairly balanced. But this is not the case. Prior probability shift is there in the data. And prior probability shift is a special case of what researchers call dataset shift. So dataset shift is the general case in which the joint distribution of the data, the joint distribution of the input variable and the output variable in the training data, which are represented as L here, is different from the joint distribution in the unlabeled data. So this is a generic type in which this true distribution in which the two distributions actually differ. So data shift may derive from very different reasons. Okay, so one of the possible reasons is that the environment is not stationary, is not static. And indeed, the operating conditions, the conditions that we are going to find in the unlabeled data were not the same at training time. So I'll make an example. Suppose that our task is to monitor the percentages of news that are about terrorism. Okay, so suppose that our training data were collected prior to September 11. Very few news were about terrorism. And suppose that our unlabeled data that we need to quantify upon, are just after September 11. Of course, there are many, many more news that are about terrorism. So this witnesses that this environment was not stationary. And indeed, the environment which is typical of the production of news is not stationary. There are also other causes for data shift. So the causes in which the process of labeling training data does introduce bias. And it's a bias that we often call sample selection bias. Let me give you a couple of examples. Okay, so one example is the one in which we introduce sample selection bias explicitly, essentially, which means we intentionally introduce sample selection bias. Assume that we need to train a classifier for recognizing the symptoms of a very rare illness, say a 1 in a million patients. Well, in this case, we need to collect the training data. But if we sample the data from the population, from naturally occurring data, we would obtain, a training set consisting of 1 positive examples and 99,900 negative data, and with this training data, we don't go anywhere, So in this case, we would try to remove many negative examples and collect as many positive examples as possible, maybe from different regions, from different hospitals, etc., to oversample the minority class. In this case, we have introduced bias intentionally. We intentionally generated a training set whose class prevalences do not mirror the real class prevalences down there. There are also cases in which we implicitly introduce sample selection bias. This is, for instance, when we use active learning in generating the training set. Active learning generates training sets which are anything other than random sets. Okay, so because of this, it is the process that inherently introduces sample selection bias. In other words, data shift invalidates what we call the IID assumption. Okay, the assumption that the joint distribution of the input and output variables in the training data is the same as the distribution in the unlabeled data. And most classifier learning algorithms are based on this assumption. So this is a further indication that using such a classifier and using classifying count in order to estimate percentages is not a good strategy. Let me show you an example of how classifying count delivers biased results. This is an example of what we call a diagonal plot, which is a plot where we plot the results of experiments, the quantification experiments. Here, the diagonal in this plot, which is displayed as a dashed line, represents the ideal quantifier. And it is the ideal quantifier because, say, it's a quantifier that when the true prevalence of a certain sample or a certain set of items is, say, 0.6%, it indeed predicts 0.6%. So it's quite evident that this represents the ideal quantifier. Let's look at real quantifiers. Okay, so this is an example of an experiment in which we trained a very fancy classifier by your favorite neural network technology, and we trained it by using a training set consisting of 50% of positives, 50% of negatives, and a perfectly balanced classifier. And this is the results. So what we show here, what we can see here is that, this classifying count based on this classifier produces very good results when the true prevalence is essentially very similar to the prevalence of the positives in the training data. But, as soon as the true prevalence of the unlabeled sample that we ask the system to quantify upon becomes a bit different from the natural prevalence in the training data, the quantification accuracy decreases. And in particular, we tend to have underestimation, when the true prevalence is higher, than the one in the training data. And we have overestimation when the true prevalence is smaller than in the training data. In other words, you may see that classifying count tends to always return, a predicted prevalence, which is intermediate between the true prevalence and the prevalence of the positives in the training data. So this occurs for both the underestimation case and the overestimation case. And this is not casual, This doesn't just apply to training classifiers with perfectly balanced data, as you can see in this picture. So for instance, even take the orange line, okay? So this represents a quantifier, a classifying count quantifier trained with 10% positives, out of the total. In this case, we have a systematic underestimation of the true prevalence. So for instance, here the true prevalence was 0.8, but the system predicts just 0.2, And of course, the overestimation occurs in the other symmetrically cases. So you might ask, are there are there methods by means of which we can do better? The answer is yes, and this plot exactly shows this. Shows a couple of true quantification methods, which are called HDI and EMQ, that perform much better across the entire spectrum, much better than classify and count. So these are not particularly fancy quantifiers. These, for instance, EMQ dates back to 2002, HDY dates back to 2013. So they are very well established methods in the literature. So one question might be, why is it the case that CC delivers biased results? And I'm going to show you an example by relying on the optimal Bayes classifier. So the optimal Bayes classifier has a formula that we all know, which is derived from the Bayes theorem, which says that the posterior probability, the probability that item X has class Y, is, can be estimated as this, or is essentially identical to this fraction. Okay. Well, when we want to train this classifier, the idea is that here the factors in the numerator are unknown, so we need to estimate them on the training set. And in particular, I want to draw your attention to this factor. Okay, so this factor PUY is unknown, so the probability, the class prevalence of the prevalence of class Y in the unlabeled data, and we estimate them by the identical quantity in the labeled data. However, just imagine that there is prior probability shift. Just imagine that, say, while here, in the unlabeled data, we have 30% of items that fall in class Y. This is in the training data, we instead have 60%. This means, that this is a bad. We are doing a bad estimation of this quantity, which will also reflect on a bad estimation of these posterior probabilities. In other words, these posterior probabilities will be all overestimated. So prior probability shift in the optimal Bayes classifiers leads to inaccurate classification results. And if you use classify and count, an inaccurate classifier will also lead to inaccurate quantification results. And they are essentially of the same type that you see here. Underestimation when the true prevalence is higher than the prevalence in the training data, overestimation in the opposite case. So this is a very graphic example of why classify and count delivers biased results. Well, the quantification literature has developed a plethora of different methods. I'm not going to go into details of these methods, just to show you, for instance, that both aggregative and non-aggregative methods have been developed. An aggregative method is a method that involves the use of a classifier. So all of the items are first classified, and then the result via some creative means. While instead a non-aggregative quantifier is a quantifier that operates in a sort of a holistic way, a quantifier that does not involve the classification of the individual items as an intermediate result. As I said, there is a plethora of different methods listed in this table, that have been developed in the, this is just a small subset of the methods that have been developed in the literature. The blue ones are the ones where me and my group were involved, but I'm not going to show them. Just as an example, an example of how a quantification method operates. I want to show you how the HDY system operates, because it's a fairly interesting example, of how a quantification system operates. So, what are the basic ideas beneath which underlie HDY? Well, the idea is that if we take a classifier, and classify all of the unlabeled data, suppose that this classifier is a soft classifier that produces classification scores from 0 to 1, where 1 means I, the classifier, I'm absolutely sure that this item falls in the class. 0 means I'm absolutely sure that it doesn't fall in the class, and intermediate values are in between. Okay, so we can take all of these scores and generate a score distribution, like the gray one you see in the lower right corner. So this is the distribution of the scores computed by the classifier. The idea is that the distribution of this distribution of scores is obtained by the contribution of the positive examples and of the negative examples. Of course, we don't know which are the positive examples or the negative examples, but we know that they follow different distribution. So they typically follow some distribution like this, So this is a distribution of the scores for the positives, and this is a typical distribution of the scores for the negatives. Okay, so if we, could estimate these two distributions, well, the idea is that we could obtain the final unlabeled distribution, by taking a linear combination of the distribution of the positives and the distribution of the negatives. Well, can we estimate these distributions? Well, yes, we can do this by k-fold cross-validation, on the training set. Okay, so if we run k-fold cross-validation of the training set, and we take the distribution of the scores, we find something like this. Okay, so the blue one is the distribution of the positives, the red one is the distribution of the negatives. So we can indeed generate estimates of this distribution and this distribution. So, well, the idea is that since, our distribution of the unlabeled scores is alpha times this distribution plus 1 minus alpha times the negative distribution, well, the idea is that we can try to generate the linear combination, which best fits the unlabeled distribution. Okay, so suppose that the best fit is obtained by taking alpha to be 0.4 and 1 minus alpha to be 0.6. Well, if this is the best fit, what we can conclude is that the positives are 0.4. So this is our quantification. We have concluded that in our test set, 40% are the positives and 60% are the negatives. Well, I hope you have just understood the gist of this method. This was just to show you, how a quantification method, which is different, from classifying count, can proceed. Applications, applications of these technologies. There are, as I mentioned, in the beginning, there are many possible ones. Well, epidemiology, we can try to determine the prevalence, the proportion, the prevalence of a given illness from, say, what we call weak signals, say, verbal description of symptoms. Okay, so this, is an example in which, from these verbal description of symptoms, we are not interested in individuals, but we are interested in the prevalence across a certain population. In market research, for instance, determining the support for a certain product from textual answers that are returned to open questions within questionnaires. In ecological modeling, for instance, people try to determine land cover mapping from satellite images, say, determining that out of a square portion, out of a photograph, that represents a square portion of the land, say 35% is covered in rivers and lakes, 40% is covered in urban areas, and 30% is covered in woods. Okay, so here typically people, what they do is they classify individual pixels, but we are not interested in the individual pixel. We are interested in the total areas, in the quantities, in the distribution of these classes. Social sciences and political sciences are similar examples, okay? So determining, say, the patterns of happiness within a certain population by analyzing tweets, or monitoring the degree of support for a certain politicians, for a certain policy, for a certain party, from social media posts. So, I mean, applications, really, you name it, So you might really wonder, is quantification applicable to my work, And the answer is, well, you have to ask yourself two questions. Question number one, does my work have to do with individuals whose membership in a class is uncertain, So, individuals that would require a classification by a supervised machine learning, And the second question is it the case that what I really care about is not which class an individual belongs, but how many individuals belong to class? Well, if the answer to these two questions is positive, the answer is yes. So quantification is applicable to your work. And indeed, it's quite curious that there are hundreds of research works published in conferences and journals. So one typical example is computational social science. I mean, hundreds of research works that use classifying count, and they do essentially because the authors are unaware of the existence of what we might call proper quantification methods, or the existence of quantification as a discipline, Of course, I mean, the caveat here is that whatever you can do with quantification, you can also do with classification technology. The problem is that quantification just allows you to do it more accurately, to estimate your prevalences, to estimate your percentages much more accurately than if you do regular classification. So something you might wonder is, suppose I want to apply quantification, should I start from scratch? The answer is luckily no. There are indeed frameworks, there are libraries for this, and one library I want to direct you is QuaPy, which is an open source framework for quantification, which is written in Python, which contains essentially everything you would need to know, but you didn't dare to ask about quantification. So it includes implementations of quantification methods, of evaluation protocols, evaluation metrics, of model selection routines, parameter optimization routines, which are explicitly oriented to quantification, and also visualization tools. So this is freely available. This is an open source, Some of our recent work we have done quite a lot of work recently in quantification. So first of all, we have published this book, that the good news is that it is open access. So if you're interested, you just need to Google for Learning to Quantify and Springer, and you can download the book for free, So we have worked at many different tasks involving quantification, such as cross-lingual sentiment quantification. So cross-lingual is when you have training data for one language, but you would like to do quantification for another language for which you don't have training data. This is indeed possible. So we have worked, and we are currently working also on quantification for ordinal classification schemes. That means when your set of classes, is totally ordered, as when you need to work on, say, product reviews, where the classes are, say, 1 stars, 2 stars, 5 stars. Sentiment quantification for Twitter. We have argued that most of the people who actually do sentiment classification on Twitter data, and there are many of them, most of them essentially mean quantification, because hardly anyone is interested in the opinion of the individual person who tweets. We have worked on quantification for multi-label classification scheme. So that's when, the same data item can belong to several classes at the same time. And also we have worked on let's say, interesting applications in the area of fair and trustworthy machine learning. So quantification can be used, for instance, for measuring the fairness of classifiers in a certain condition that fairness people call under an awareness of sensitive attributes. You know? And why are fairness and quantification tightly linked? You know, they are tightly linked because quantification has to do with aggregate data, and fairness also has to do with aggregate data proportion. Say, in a certain set, in the set of individuals who were granted, say, a loan via machine learning algorithm, what is the proportion of women? What is the proportion of colored people? So, you know, fairness has inherently to do with proportions, and quantification is very useful for that too, you know. So other ongoing work we are currently doing is doing, say, quantification for seabed cover mapping, you know, for underwater, you know, for the way that the bottom of the earth is covered within different natural species, such as coral or other, you know. So this allows you, for instance, to monitor how the population of coral is evolving in polluted areas, you know. So also, you know, we're working on tailoring quantification methods to different types of dataset shift. One of the problems with the current quantification literature is that up to now, quantification has, in a sense, overfit one specific type of dataset shift, which is prior probability shift. But there are many other types of dataset shift that require our attention when, as far as quantification is involved. And also we are working on using quantification for estimating the accuracy of classifiers, on estimating what is the likely accuracy that a classifier is going to have when it will be asked to classify data that are characterized by dataset shift, data that are radically different from the data that the classifier was trained on. And of course, I mean, among the potential topics, you can put your favorite topic here. So it means that, you know, we're very open to collaboration with other groups. So if you think you have a problem setting which would benefit from using learning to quantify, well, just drop me an email, and maybe this might be the start of a nice collaboration. So conclusion, you know, quantification is a relatively little known, you know, and unexplored task in machine learning, but one that has many potential applications. So many applications applications are possible whenever membership of individual items in classes is uncertain, so there is a need for supervised learning, and whenever the aggregate results as opposed to individual results are the real items of interest. There are many research problems still open. You know, I don't have the time to talk about them, unfortunately, but I just want to say that if you're interested in quantification, there are a lot of resources on the web. You know, I've mentioned an open source framework software, you know, but you know, there's also literature. You know, for instance, you know, there is an upcoming workshop on learning to quantify at the European Conference on Machine Learning in September. Analogous workshops LQ 21 and 22 have occurred, so the proceedings are online. And there is also a shared task, a data competition, which is being organized at CLE. It has, the first edition has run at CLE 22, and it's going to be repeated, luckily, hopefully in 2024. You know. So final slides, conclusion, you know, what is the takeaway message? You know, my takeaway message is, you know, the fact that there is a growing awareness, you know, that quantification is going to be more and more important, you know, and it's going to be more and more important because given the advent of big data, you know, new application contexts will spring up, you know, will emerge, in which we will only be able to afford analyzing data at the aggregate level rather than at the individual level. So this concludes my talk, and I'm happy to take questions, if any.
Yes,
I just
thank you.
want to mention that if you're interested in the slides, you can download the slides at this URL.
Great. So as time is passing and we normally stop at this time, I directly go to our participant lead question. Number one was about the recording that will come in the next days after Fabrizio, as our speaker, has checked it. And then you find it on the AI for Media. So I give here the answer. And now to you, Fabrizio. It's from Alessandro. Yep. Ciao, Fabrizio. Great talk. You mentioned that the world is not stationary, but this means that quantification might change with time. Is there any way to detect when a quantification has changed and update the results of a previous quantification task without doing a full retraining from scratch?
Okay, let me display this plot again. So it's true that the environment is not stationary, and but let's say quantification methods try to adapt to this evolving environment. Okay, so when you train a quantifier, it's a quantifier that tries to be, in a sense, ready, to tackle the different possible situations that might occur in the future. So what we are looking at with quantification methods is robustness to different possible changing conditions. Of course, access to future labeled data would improve the situation. So this is a topic in which the topic of learning to quantify intersects the topic of so-called continual learning. The difference between, well, both learning to quantify and continual learning, put an emphasis, on the fact that conditions change in the future. But in continual learning, in general, you often assume that you have some access to labeled items in the future, and this is different in quantification. In quantification, you normally assume that you don't have access to labeled items in the future, So indeed, there are intermediate situations between the two. It's quite clear, that if we do have access to individual future data, label data, the performance of quantification can improve. But anyway, so this is an intermediate territory between these two areas. I don't know if this answers your question, Alessandro.
Well, I talk now for Alessandro as he cannot speak. So let's say this was a great answer, and Alessandro can say no. But as time has passed, and I want to thank everybody being here, and especially you, Fabrizio. And thank you. Please check the AI for Media project website for the recording if you feel like, and have a great afternoon. This is here. I'm in Cologne, sunshine, so I hope out there is also sunshine. And thank you. Talk to you, Fabrizio. I will send you the email with the link.
Thank you very much. Thank you very much, everybody who attended.
Yes, thank you. Bye-bye.
Bye. Bye-bye.